Hello and welcome back to another episode of Mr. Walker's Chemistry. Today we're going to be talking a lot about electrons, and I titled this Further Down the Rabbit Hole because this is where chemistry gets really, really weird and begins to break more into the realm of physics. So I'm going to try and go slow on this video. We're going to do a little bit of review of what an electron is, what an ion is, and then we're going to be Alice tumbling down the rabbit hole of how electrons work. Okay, so the objectives, you should be able to identify how many electrons an atom has. As I said, this should already be reviewed for you guys. We've done it many times at this point in the videos and probably in class. So now we need to understand, how do we find an electron? All right, an electron is a piece of matter. So it's like if I scattered, marbles all around the room, you should be able to find those marbles. But maybe we can refine it a little bit. Instead of you searching the whole room for days trying to find a single marble, maybe we can define an area where you might find it, like under the desk. Okay, that's what we're trying to do here in this video. And it's going to get really funky because, it's not just like saying under the desk. It's a little bit different than that. So just a quick review. All right. This is what our typical atom looks like up to this point. You have a nucleus with protons and neutrons in the middle. Okay, so represented by green and red balls in this case, and electrons going around the outside in what Bohr called orbits. So Niels Bohr, from the History of the Atom video, he was one of the first to figure out how the atomic structure really is, and he kind of combined efforts from Rutherford and Thomson together and created this model. So we've got blue balls, which represent electrons, going around in orbits around a central nucleus, like planets around the sun, if you want to think of it that way. Okay, if you have a neutral atom, which would be a non-ion, okay, that means that you have equal number of protons and electrons. Okay. However, if you have unequal numbers, we generate an ion. There's an entire video about ions, so if you've forgotten, please go back and rewatch that video. So if you know how to do an ion, okay, you should be able to figure out the charge of this atom. I'll help you out and refresh your memory. Let's first count how many protons we have. So I can see that we have 4 protons. Okay, green ones are protons. All right, now let's count our electrons. We have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 electrons and only 4 protons. Let's figure out the charge. So charge, I'm just going to put C, is protons minus electrons. So charge in this case will equal 4 minus 8, which of course is -4. So we have a -4 charge on this atom. Okay, this is a formula you should memorize. Charge equals protons minus electrons. All right, so moving along then. Got a lot of information here just to learn. I would not write down all this information. Okay, so again, in the History of the Atom, Niels Bohr came up with these orbits, and he didn't do this just because it, makes the atom look all pretty and stuff. He did it because he actually had scientific observations of the electromagnetic spectrum, which includes light, microwaves, gamma radiation, X-rays, etc. And he observed hydrogen atoms, and he put energy into them, and he found that when you add energy to an atom, that they will then give you energy back out of the atom. So he was able to quantify this energy using physics. There are a lot of formulas in physics that involve light and figuring out how fast it's moving, and it's a wave, so it has what we call a wave length and a frequency. Okay, so if I have a wave, just a little physics lesson here. If I've got a wave, okay, it has a frequency, which is how often do I hit a peak. All right, that's the frequency. How many peaks in a second? All right, and the wavelength, which is the distance between the peaks. Okay, and so all light has this. It moves in a wave where you've got a frequency and a wavelength. And using that math, you can find the energy. Okay, so energy is actually equal to the wavelength, which is this symbol, times the frequency, which is a V, a funky little V. It's like a cursive V. Okay, so wavelength is represented by this like upside down Y, and frequency is a V. So energy equals these. So when Niels Bohr observed this, he measured the frequency, he measured the wavelength, he figured out how much energy was coming from it. So he quantified it. Quantify just means to calculate or to give a number to. So he gave a number to this and developed what we call the quantum mechanical model, which you can see over here. Okay, this is the quantum mechanical model where you've got a nucleus in the middle and different energy levels that we call orbits. These are very, very similar to pretty much all the models you've seen so far. So you can see this diagram closely resembles this other diagram here. Okay, they're very similar, but this one we've assigned some numbers to. We've quantified these orbits. So we have 2 orbits here and 4 orbits here. All right, so these levels, so 1, 2, 3, and 4, which you can see is also n equals. It's the same thing as saying n is the same thing as saying energy level. These are called quantums, or values of energy. The higher the number, the higher the energy. So if I have an electron out here in energy level 4, that means that that electron contains a lot of energy. An electron in energy level 1 would indicate that it has very little energy. All right, so the electrons, as you can see in this diagram, they go around these energy levels, okay, as Niels Bohr put it, and that these 2 electrons on the inside have less energy than the 6 electrons out here. All right, these energy level numbers, 1, 2, 3, and 4, are called the principal quantum number, or PQN for short, principal quantum number. Okay, so we have principal quantum number 1, principal quantum number 2, principal quantum number 3, and principal quantum number 4 in this diagram. All right, we're going to use these a lot in class. We're going to use these a lot because these are used as the first step. These are the first step towards finding where an electron is. All right, so this is like if I walk into a room and I'm looking for those marbles that I've scattered everywhere. All right, instead of scouring the entire room, I can just say, okay, I'm going to go look under the desk. It simplifies my search. If I don't give you a principal quantum number, it's like me just telling you to search the entire room. It'll take you a lot longer to find an electron. So this makes it really easy. As an analogy, you can think of these numbers like the very first number in a zip code. So if you were trying to tell somebody where you live, instead of just saying, I live in the US, or even I live in Maryland, and them having to search all over Maryland for you, you could say, I live within the zip code that starts with the letter 2. So that's going to tell them, that you live in a certain part of Maryland. Okay, won't get them much further than that, but it's a step in the right direction. So we're going to keep adding things to our zip code here. All right, so a little bit more history. Hopefully you remember from the history of the atom video that we found that Bohr was incorrect. He did all his experiments solely on hydrogen atoms, but when scientists applied that knowledge to other elements, like even helium, just the next one down on the periodic table, it didn't work. Bohr's observations didn't stand up, and his theory didn't stand up to scrutiny. That's what science is all about. So we refined it, okay? And Erwin Schrödinger came along, and he said, well, what if they're not really in orbits? What if they are more like in a cloud, and they just go around, but they stay within an area. So instead of an electron following right along this path, okay, what if it kind of goes in between and it goes off the line a little bit and it comes back and it goes out here and then it comes back in? All right. So what if instead of like a planet around the sun, it's more like a bee around a hive? Okay, it stays near the hive, or the nucleus in this case, but it goes kind of all over the place because they're 3D, they're not 2D. All right. So we went from this model, which is the quantum mechanical model, to this model, which is either the quantum mechanical model updated or the electron cloud model. And I do want you to note that with this, we changed some vocabulary. We went from orbits to orbitals. So orbit, orbital, orbit, orbital. Still have the nucleus in the middle. We just have all these things going around it. So we're going to explore more into these orbitals. Now, these numbers you see here, 1, 2, and 3, are still our principal quantum numbers. These are our first number of the zip code, and the SP that you see here represent the second letter in our zip code. Okay, so we've got number, then letter, and we're getting closer. You can see that if I say just orbital level 2, well, you can be anywhere inside the brown or the red. But if I say 2s, you can only be inside the brown. So it really, really simplifies and narrows down where the electron could be. So, again, this new quantum mechanical model developed in Schrödinger by 1923 is still the best we have so far. Yes, it is old. It's almost a century old. But scientists really haven't figured out a whole lot more about it. But this does create some problems. There are lots and lots of problems with the electron cloud model, which scientists are trying to figure out. For instance, the very first problem is this one. It's called the Heisenberg uncertainty principle. Werner Heisenberg, way back in 1920s, determined that he could not find the position and momentum, or speed, of an electron at the same time. And that might seem weird. Okay? How can you not know how fast something is going, but know where it is, or know how fast it's going, but not where it is? That seems really strange to us, because most of the things that we can see, we can also tell where they are and how fast they're going. Alright? So, I'm going to give you a couple of examples. The first one is this. This is really, really a cool visual illusion. If you look at any given cross-section, okay, so for instance, let's look at this middle one. If you look at the middle one, it looks white, and all the dots around it look gray or black. All right. Now try and focus on the one to the left of it. It turns white, and the previous one turns gray or black. This is very much like what we're talking about with the electrons. So if you imagine these white dots to be electrons, you can either know whether it's white or black. But when you look at it, it's either white or black. It's really weird, okay? It's kind of one of these, it's a visual illusion, but it's very applicable to electrons. It's kind of a good way to think about what we know about electrons. Another example that may be more applicable. You're driving down Mountain Road here, and you are on your phone. Okay, you're driving the speed limit, 40 miles per hour, and you're on your phone with your friend at Five Guys, and your friend says, "Where are you?" And you say, "I'm in front of the volunteer fire department." And then he says, "How fast are you going?" You say 40 miles per hour. And then he asks where you're at again. And you're no longer in front of the fire department. You're now down the road in front of the Tree Unlimited sign or something. Okay? This is kind of what we're talking about. Your friend can either know how fast you're going or where you are, but not both at the same time. All right? So, the best we can do with electrons, since we can't really narrow down exactly where they are or exactly how fast they're going, The zip code analogy works well. All right, we can find the generic area that an orbital exists, like the zip code for Pasadena. That tells people that you're generally in Pasadena, but it doesn't tell them where in Pasadena you are. It's just like they have a good chance of finding you somewhere in Pasadena. They just need to look forever to find you. Okay, this is what physicists do. Okay, and they're still working on these problems, especially with the new CERN collider, super collider in Switzerland. Okay, they're smashing electrons and protons together. And also with supercomputers. There are millions of computers out there working to try and figure out certain things about electrons. And it's challenging. So if you're interested in these subatomic things and want to learn how the universe works, you can become a particle physicist. They work on these sorts of things. All right, so back more about our atom in general, the 3D nature here. Okay. It's really easy to think about atoms as being 2D because we're always looking at pictures like this one or the ones that you've seen previously. These are all 2D. All right, but really they're 3D. Okay, matter is 3D. It's more like a basketball. All right, and we got to find what's inside the basketball. Okay, so somewhere within each of these different colors, the purple, the brown, the red, or the gray, we have a 90% probability of finding an electron if I tell you where an electron is. So we note that we keep the principal quantum number, in this case 1, 2, or 3. That's as high as we're going, although we're going to go up to 4 or 5 in this class. And the next thing, this letter is like the next value of our zip code. It tells us the shape. Okay, these letters here that you're seeing, S and P, tell us the shape of the orbital. We're going to go more into this now. All right, so we've got principal quantum number is the energy of the electron. The letter tells us the shape. Okay, where might we find this thing? All right. So, S orbitals. S stands for sharp in the scientific world. All right, and this is how they look through a spectroscope. It's a special type of instrument that measures energies. And that's fine and all, but you're never going to hear me say, let's look at the sharp orbital. Okay, we're going to say look at S orbital. And just for normalcy, let's just keep it simple. That's the good principle, the KISS principle. Keep it simple, stupid, right? All right. S for sphere. Okay, S for sphere. And this is an S orbital here. It's spherical. It's very easy to remember that. Okay, and this is the most basic shape of an orbital. For each principal quantum number, remember the 1, 2, 3, and 4, there can only be one S orbital. So let's look at our diagram here and pull this up so we have an example. So you'll see that for principal quantum level number 1, there is one S orbital, one sphere there. And for the 2 orbital, we only have one sphere. Okay? Then for 3, there's another sphere. So for each principal quantum number, you have one sphere. And they get bigger and bigger and bigger as you go out because they have higher and higher energies. All right. Next, we're going to talk about this p orbital. Okay. So p orbitals are a little bit more complex. P stands for principal in the scientific community, but I like to think of P for paddle because they're shaped like a paddle for like a kayak or something. All right. These look like paddles for a kayak. And for each principal quantum number, there can be 3 of them. There's one in the x direction, so if this were like an XYZ graph like you might have in math, okay, so x goes left to right, then we've got y, which is vertical, and z, it looks diagonal here, but it's actually like front to back, okay? Remember, these things are 3D, so you've got 3 directions, left to right, top to bottom, and then front to back, okay? And so when we pull up our diagram that puts them all together, you can see that we have that same thing. We've got an X, a Y, and a Z. And these are all types of 2p orbitals. So there are 3 2p orbitals. One in X, one in Y, one in Z. Now, the first principal quantum level, in other words, when you have 1, the number 1, there's no such thing as 1p. Okay, that zip code does not exist. 1p does not exist. You can only have 1s. Then you can have 2p, 3p, 4p, 5p, etc. After number 1, you can have as many p's as you wish. And the last one we need to learn about, which is new, you haven't seen, is the d orbital. Take a minute and look at these. They look really funky. This is why they're hard to incorporate into diagrams. All right, so for high school chemistry, this is as far as we're going to go. We're going to go to D. When you go to college, you're going to learn about F orbitals, F for fundamental, okay? So you've got S, P, D, and F. We're only going to go as far as D, so S, P, and D. And as you can see, these are pretty weird. They're wonky. D stands for diffuse, not important, okay? What is important is that you know the shape. So a name to give these to help you out would be double dumbbell, okay? Like dumbbells that you lift weights with. They've got the balls on the end where it's thick and the handle in the middle. That's kind of what these are like. So you can imagine that you've got one dumbbell going that way and one dumbbell going this way, so double dumbbell. And the other thing is donut holes. A lot of people think of donut holes because it looks like you've got 4 donut holes stuck together. So if that helps you, go for it. Now, d orbitals exist at principal quantum number 3 or energy level 3 and higher. And there are 5 of them. 1, 2, 3, 4, and 5. Okay. Quick review then. S, there is one S, can exist at any energy. There are 3 P's. They can exist at energy level 2 and higher. And there are 5 D's, and they can exist at energy level 3 or higher. So if we draw an atom here, okay, so this will be my nucleus, and around it we're going to have energy levels. Whoops, let me redraw that. That's not very good. Apologize. We're going to have these energy levels. Okay, so we've got 3 energy levels. Energy level 1, 2, and 3. Maybe it's easier if I go back to, let's get this drawing here. So in this drawing, we've got energy level 1, 2, and 3. Energy level 1 can have S, and that's it. So I'm going to put a little S underneath here. Energy level 2 can have S or P. Energy level 3 can have S, P, and D. Energy level 4 can have S, P, and D. And then when we get to energy level 5 out here, you can have S, P, D, or F. And we're not going to do F, so don't worry about F, okay? It's just for that extension for those of you who are curious. All right. So finally, the last thing about electrons. I know it's been a lot. The Pauli exclusion principle. This actually simplifies our work a lot. Okay. Mr. Pauli found that electrons will spin. So just like the Earth around the Sun and the Moon around the Earth, they spin. All right, and they either spin one direction or another. Can't really say clockwise or counterclockwise because, again, it's 3D. They can spin in all sorts of different ways. So instead, he said they are either plus 1/2 or minus 1/2. They either have a positive spin or a negative spin. Simple enough. How does this help us? Well, it helps us because he said that you can only have 2 electrons in the same orbital, and that they must be spinning in opposite directions. Think about that. Think about it. Imagine an S orbital, a sphere, and in it you have no electrons right now. So you've got an empty basketball. Now we're going to throw a BB inside that basketball, just one. And that BB is going to bounce around all over the place, and it's going to spin in one direction. That's fine. We can do that. All right. Now we're going to throw another BB in there. So now we've got two BBs representing electrons inside of our basketball, which represents an s orbital. They're going to be bouncing around in there like crazy. However, they must spin inside the basketball in different directions, or they don't cancel out and the atom falls apart. All right, so this leaves us with three options for what can be inside an orbital. Technically four, because you can have no electrons inside an orbital. All right, one electron with a plus 1/2 spin, one electron with a minus 1/2, or two electrons with opposite spins. It is not possible to have three electrons, because then that means two of them will have the same spin, which is not possible. Or if you can't have two with the same spin. It doesn't work. So to summarize the rule, you can only have two electrons in each orbital with opposite spins. This is important. Write that down. You can only have two electrons in each orbital. Great. Well, now that makes our zip code. That gives us our last couple of numbers. Okay, so you've got principal quantum number or energy level, then either an S, P, or D for the shape, and finally a number to represent the electrons or the number of electrons in that orbital. Okay, so for example, we're going to get a lot into this in future videos. You could have a 1s1, which would incorporate these two, or a 1s2, which would be this one, because you have two electrons versus one electron. Okay, so we're going to get a lot more into that. If you don't get it this time, don't worry too much. Maybe just watch it one more time, but we're going to get a lot more into this. So putting it all together, our quick review. Bohr was completely incorrect about orbits, but he had the right concept about principal quantum number or energy level, so that stuck. Erwin Schrödinger came along and updated it to explain how other things work, other atoms work. He said that you have orbitals with shape of S, P, or D. There can only be one s orbital per energy level. There can only be three p orbitals per energy level, starting at energy level 2. There can only be 5 d orbitals per energy level, and they don't start until energy level 3. At most, each orbital can only have 2 electrons in it. All right? So take your time with this. You may not get it the first time around. It's a lot to know. Really focus this video on learning principal quantum number and the orbital shape and memorizing how many orbitals you can have with each thing. We're going to start applying this to chemistry and to the periodic table in future videos, so it should become a lot more simple to understand for you. All right, hope you learned something, and I'll see you next time.